Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, so we have learned about scientific notation. We have learned about positive and negative exponents and some of the basics of exponent rules. Today, in lesson 8.2.4, we are going to learn how to do some different operations with numbers that are in scientific notation. Okay, and by operations, I mean we're going to learn how to multiply, divide, and get a little bit of a taste for adding numbers that are in scientific notation. All right, so scientific notation is an application of exponents and the base 10 system. It is very useful when writing very large numbers, like the distance to Alpha Centauri, which is 4.13 times 10 to the 16th meters, or the radius of a hydrogen atom, which is 5.29 times 10 to the negative 11th meters. But what if you wanted to know how many times larger the distance to Alpha Centauri is than the size of the hydrogen atom? How would you calculate this? What if you wanted to add or subtract two numbers written in scientific notation? In this lesson, you will learn how to do these operations with numbers written in scientific notation. All right, so let's start off with a couple of whales. A typical dwarf sperm whale, the planet's smallest whale species, weighs about 3 times 10 to the second power pounds, which is translated into about 300 pounds. A blue whale, which is the largest whale on the planet, the largest mammal on the planet, largest anything, I think, on the planet, might weigh about 4.5 times 10 pounds. 4.5 times 10 to the fifth is 4.5 times 100,000, so that's 450,000 pounds. And we know this because they went and they built the largest scale ever found, and they encouraged a blue whale to hop onto it, and everybody stood around and watched as the numbers, no, they didn't, right? They're estimating. But it's probably a decent estimate. Scientists know what they're doing, I suppose, right? So yeah, 450,000 pounds for a blue whale, however they measured that. Estimate about how many times heavier a blue whale is than a dwarf sperm whale without using a calculator. Okay, they are telling us in a few of these problems to not use a calculator, and I'm like, ooh, this is going to be tricky, but we might be able to get there using a little bit of mental math if we approach it the right way. So just to give you an idea of what kind of a problem this is, because it's like, how many times bigger? What are you supposed to do when that's the question? Okay, or how many times heavier in this particular situation? So what I did is I started thinking about this and started thinking, all right, if we take this, how many times bigger is this than that is another way of saying, what would you multiply times 300 to give you 450,000 for an answer? So this ends up turning into a division problem. And 450,000 divided by 300 ends up being about 1,500, or exactly 1,500. So how many times heavier or how many times more ends up being the question that we ask when we are dividing, okay? So let's do this now in scientific notation. So we know that the blue whale is the heavier, 4.5 times 10 to the fifth power, and we're going to divide that by the sperm whale's weight, which is 3 times 10 to the second. So using commutative property, we can break these up into two different fractions. One fraction will involve leading factors, 4.5 over 3. That gets multiplied times this fraction, which has the powers of 10, which would be 10 to the fifth divided by 10 to the second. So now 4.5 divided by 3, some of you could probably figure out what that is. 45 divided by 3 is 15. So 4.5 divided by 3 is going to be 1.5. So that's going to end up being 1.5, and then 10 to the fifth divided by 10 to the second. We learned in our previous lesson that when you divide those, you take 5 minus 2, and you get 3. And so this ends up being 1.5 times 10 to the third power would be the number of pounds. No, that's not pounds. That's the number of times. So we're just going to leave it as a number. And does this match the 1,500? I think it does because 10 to the third is 1,000, and 1.5 times 1,000 would be 1,500. So let's just go back to this. When you are doing division with scientific notation, set it up as you see it here, and we're going to take this, and this will be one fraction, leading factors. This will be the second fraction, the powers of 10, and then we'll simplify each one of those and then put them back together for scientific notation. And then there's another type of a problem. There are about 1.8 times 10 to the 21st molecules in 1 gram of table sugar. Why they decided to give us the, what do we call that? The molecular structure of it? I don't know, but that's a molecule for a table sugar. 6 parts carbon, 22 parts hydrogen, 11 parts oxygen. Okay, so a baker uses 8 times 10 to the second grams in a recipe for cinnamon pastry. So that is 800 grams, right? But I don't have a clue how many molecules that is because that's a big exponent right there. So if we just thought about it this way, if I said there were 18 molecules in 1 gram and you had 10 grams, wouldn't you take 18 times 10 to give you 180 for your answer? So we're using the same approach. If there are this number of molecules per gram and you have this number of grams, you have to multiply those two numbers together in scientific notation. So how are we going to do this? Go ahead and set that up and then unpause for the reveal, where I'm going to use a little commutative property and I'm going to pretend like the parentheses are not even there because all we're doing is multiplying. 1.8 times 10 to the 21st times 8 times 10 to the second. Let's use commutative property to rearrange those so the leading factors get multiplied together first, 1.8 times 8, and then 10 to the 21st times 10 to the second. Well, 1.8 times 8, I'm going to round that off. 1.8 is almost 2. And 2 times 8 is 16. So that's pretty close to 16 times 10 to the 23rd. Because 10 to the 21st times 10 to the second will add those exponents together. But that's not in scientific notation, remember? We got to have your first factor be a number between 1 and 10. So if I take 10 away, or divide that by 10 and make 1.6, oh wait, do I do that? Yes, let's do that. Let's take, and we did this the other day, I'm going to do this in green. Let's take this and make 1.6 times 10, and then multiply that times 10 to the 24th. So that these guys can now join up together because that's 10 to the first. And so that's going to give us, wait, hold on, I didn't write that right. That was supposed to be a 3 there, right? 10 to the 23rd. And so that ends up giving us the number of molecules would be about 1.6 times 10 to the 24th. Now, when you use a calculator, this is often displayed. If you've got a scientific calculator, go ahead and do this problem using scientific notation. And let me see if I can get that looking up here. That's not what I want. Let's take, what was that again? It was 1.8 times 8. So I'm going to do that in the first parentheses, 1.8 times 8, end parentheses. And I'm going to take that quantity and multiply it times, that was 10 to the first, so I'll just leave that as 10, times 10 raised to the 23rd power, end parentheses. Let's see what we get for our answer. You got 1.44. So I had estimated it to be about 1.6, but I rounded that up to 2. So it's really 1.44 e plus 25. That's similar. Wait. Oh, wait, why 25? It shouldn't be 25. Or should it? Hold on for a second. I'm having a brain fart. I'm going to come right back to it. Hold on. All right, let's just start this whole thing over. I'm going to start from the beginning of the process right here. 1.8 times 10 to the 21st. No, parentheses, people, parentheses. 1.8 times 10 raised to the 21st power. Stop it. Raised to the 21st power. Stop it. Times, what was that again? 8 times 10 to the second. 8 times 10 raised to the power of 2. Okay, this should give me the correct answer. That's what we run. So 1.44 e plus 24 is very similar to what this calculator shows. What do you think that e is telling you? Okay, look at what we have for our answer when we used the proper processes. Look what we have right there. What is the calculator telling you? Well, if you're thinking that e really means 10 to the power of whatever that number is, that is exactly right. The correct answer is 1.44 times 10 to the 24th. If you didn't round that 1.8 to a 2 and call that 16, which we then changed to 1.6, okay? That was an estimation. That is the actual answer. So when you see that E pop up, and I'm sure every one of you at some point on a scientific calculator has seen that E pop up sometime, you didn't know what it meant, that was the calculator's way of telling you an answer in scientific notation in the only way the calculator can do it. And that is, this is your leading factor, the 1.44, and this implies that you're multiplying that quantity times a power of 10 that's been raised to an exponent of 24, okay? The scientific calculator here, plus in there, don't know why, but otherwise it's the exact same thing. So I would imagine many different calculators show this in slightly different ways. But they all have that E sort of a thing in common to imply that that number there is the exponent for the power of 10 that's being multiplied times that first number that you see in the window. All right, so this says without using a calculator, have fun, okay? Find 1.75 times 10 to the 20th times 6.01 times 10 to the 14th. Put once without a calculator, do some estimation, and then do it again with the calculator to see what you get for your answer, to see if you are in the right ballpark, okay? Take some time, work through this, remember the process, use commutative property, get the 1.75 and the 6.01 together, get the 10 to the 20th times 10 to the 14th together, and then start working through the process, okay? All right, see how you did. We're going to start by copying the problem down exactly how it's written. Then we will do some rearranging to get our leading factors together in one parentheses and our powers of 10 in the other. 1.75 times 6, that's 1 3/4. So if I use distributive property, 1 times 6 is 6, correct? And then 3/4 of 6 is going to be like 4.5 or something. I think, yeah, it's about 4.5. So this should be like about 10.5. So that's what, about 10.5 multiplied times, add those exponents together. Why did I put that down so low? That should be up below, right up there. Okay. That would be 10 to the 34th power. But that is not actually completely correct because that's not in scientific notation, correct? So what I'm going to have to do, let me even move this up a little bit more, is I'm going to have to take one of these powers of 10. Actually, I don't have to show the work. We can just talk about it. If you move this decimal one place to the left so that it becomes 1.05, we are essentially dividing this by 10, and we need to take that power of 10 and move it over into here and have it join up with your 10 to the 34th. So that becomes 1.05 times 10 to the 35th. So now when we use the calculator for this process, let's go ahead, clear everything out. What was that? It was 1.75, 1.7, stop it, parentheses, 1.75 times 10 to the what power? To the 20th power, end parentheses, multiplied by a new scientific notation, which starts with 6.01, 6.01 times 10, and this one I think was to the 14th power, right? 14th power n parentheses. Let's hit the enter button and see what we get. We get 1.05175 with an exponent for your power of 10. That is, oh, I bet that means positive 35. If it was a negative exponent, it would show minus 35. So it's a positive 35 exponent. So let's take a look. Is that what I showed right there? Yeah, that's what we got right there. So notice I had rounded this off, so that's why it's 1.05 instead of 1.05175. So that would be the exact answer for this particular problem. All right. The average distance from the sun to the earth is 1.488 times 10 to the 11 meters. I wish they would just do miles or kilometers. I mean, nobody's measuring it. Well, I guess maybe scientists are. All right, so we'll keep it in meters because that's what they're saying. 1.488 times 10 to the 11th meters. If the length of an average paperclip is 3 times 10 to the negative second meters, which, by the way, remember, a meter is a little bit more than a yard. So you're talking about a fraction of a meter for the length of a paperclip. So that's what we're talking about here. And I think 10 to the negative second meters is a centimeter. So this is saying it's about 3 centimeters long. Okay? So 3 times 10 to the negative second meters is the length of a paperclip. How many paperclips would you need to connect from Earth to the sun? Okay, another wonderful, because okay, whatever. Paper clips to the sun. What fun. All right, so this is a division problem. This is kind of like how many of these can you fit into there? So if I were to give you this basic 6 divided by 2 is equal to 3, another way of asking a division problem is how many of these can you fit into that? You can fit 3 2s into the 6. So how many paper clips would you fit between planet Earth and the distance to the sun? So we're going to have to take the distance to the sun divided by the length of the paperclip will tell you the number of paper clips you can fit. So this divided by that is going to be how you solve the problem. Go ahead and see if you can figure out the answer to that using the steps that we've already learned for dividing with scientific notation. Alrighty, let's see how you did. And I'm guessing at least half the people just decided they're going to wait for me to do the reveal and copy me down, which I guess is okay because this is all brand new. So we would start off by doing the division problem, where you would take 1.488 times 10 to the 11th divided by 3 times 10 to the negative second. Well, we're going to take this part and do the division, and I would suggest rounding that up to about 1.5. So you can do it a little bit easier. That ends up being, oh, I'm doing a reveal, aren't I? Oh, I guess I'll do it this way. So this times that, and this is like 1.5 divided by 3, so that's going to be about 1/2, because 1.5 is half of 3, right? And then 10 to the 11th divided by 10 to the negative second, when we are dividing powers with the same base, you're going to subtract the exponents, and this becomes a subtraction with a negative. So you do KFC, that's going to become 11 plus 2, so it becomes 10 to the 13th power. However, this is not in scientific notation because the leading factor is not a number between 1 and 10. So I'm going to borrow one of these powers of 10 and multiply it times this. So that's going to become a 5, but then this is no longer 10 to the 13. This is now going to be 10 to the 12th power. So that would be 5 times 10 to the 12th power paper clips you could string together to get from planet Earth to the sun. And those last few are really tricky too because, you know, attaching it to the sun, I hear it's pretty hot there. All right, this last bit of work, is this the last, final? Not quite. This last bit of work is showing how to add these together. And this is a little bit tricky, and it's going to take some time. We're just introducing you to the idea that you can add, multiply, and divide, and for that matter, subtract numbers that are in scientific notation. Once you know the pattern and you know what to do, you can do these operations without too much trouble at all. Of course, if you use your scientific calculator, it makes it even easier to do, but you know, you can do it paper pencil. There is a logic to it all. So here's the premise. Jeremiah wanted to do the following problem. However, he was not sure how to get started because the numbers were in scientific notation. He knew that if he wrote them out in standard form without scientific notation, then he could line up the numbers with the same place values and the decimal points and add them together. He does not want to do that, however, because he doesn't want to have to write all of these zeros. He is worried that he might just get more confused if he did write them all out, which I don't think he would. That's not a lot of zeros, but whatever. Work with your team or on your own to find a way to add these numbers required without rewriting them in standard form. Here is the problem that Jeremiah wanted to solve. Okay, so the average distance of each of the first 5 planets from the sun is shown in this table below. Mercury is the closest, then Venus, then Earth, then Mars, then Jupiter. The question is the distance to Jupiter from the sun more or less than the combined distances of all the other planets? Okay, so you take the distance from Mercury to the sun, the distance from Venus to the sun, from Earth to the sun, and Mars to the sun, and add up all of those distances. Will that be greater than 4.836 times 10 to the 8th? So what we need to do here is we need to figure out a way to add these without going into standard form. Jeremiah doesn't want us to do that. So what needs to be done? Let me back things up. Okay, when we are adding variables, when we are adding variable terms together, like let's say 2x plus 3x. This is literally 2 times whatever x is, and this is literally 3 times whatever x is. So when we add those together, we just add the coefficient parts and keep the variable parts. So it's kind of like when we do factoring, we would factor out the x, and that becomes 2 plus 3, which is 5. And so x times 5 is the same as 5x. So we've just learned the shortcut where we add the exponents and we keep our variable. This, by the way, is the exact same thing when you're adding fractions together, the logic behind this. It all comes down to distributive property and factoring. Well, let's say x was a power of 10. If this was 2 times 10 to the second power plus 3 times 10 to the second power, this is really 5 times 10 to the second power. Do you believe me? 2 times 10 to the second power is 200. 3 times 10 to the second power is 300. When you add those together, you get 500, right? This absolutely works. So in order for us to add all 4 of those numbers together that are in scientific notation, we're going to have to get the powers of 10 to be exactly the same. Since this is a power of 10 to the 8th power, I would recommend converting all of these out of scientific notation into a form where they're all being multiplied times 10 to the 8th power. Okay, so let's get to it. Let's start with 5.79 times 10 to the 7th power. If I want to borrow a power of 10 from 5.79, I'm going to have to move the decimal 1 place to the left and then move that power of 10 over to here to make that 10 to the 8th. So that becomes 0.579 times 10 to the 8th. Same thing here. If I move this 1 place to the left, I'll be taking a power of 10 away from 6.72 and then putting it over here with the other powers of 10 to make that 0.672 times 10 to the 8th. Move this guy 1 place to the left because we're going to divide out a power of 10 and then convert it over to here. That becomes 0.930, and I'm going to add the 0 there so that when we add these together, you'll have a digit in the thousands place for all of them. And then this one doesn't have to be converted at all, so it's going to stay as 1.416 times 10 to the 8th. So please go ahead and use your calculator for this. This is totally okay. Go ahead and add all of these decimal numbers together, and then it'll be that quantity times 10 to the 8th. And then you determine and write a little statement to answer this question. Is the distance to Jupiter more or less than the combined distances of the first 4 planets? Is the total sum of this greater than or less than this number in scientific notation. Okay, go ahead and take some time and add those together and declare your answer. All right, let's see how you did. When I added all those up, I got 3.597 times 10 to the 8th. This is 4.836 times 10 to the 8th, which makes the distance from Jupiter to the sun is actually greater than the combined distances of the first 4 planets. What a lot of fun. Okay, this is nothing I will be testing you on. This is rather complicated, just introducing you the idea of it. I may test you on the multiplication and division. I feel like we should be able to do that. But this just takes it to another level. It's a little bit confusing, so I'm just introducing this part. All right, last task. Here you go. I told you I'm probably going to test you on division problems and multiplication problems, not so much on addition problems. But I want you to see if you can do all of these, okay? Now, if you end up cheating and using your Google Scientific Calculator, I'm going to be equal parts annoyed, but also impressed because you're using your resources, right? But I would rather you try and figure it out and then use the Google or your scientific calculator to see if you're getting the correct answer and use it as a tool to check rather than relying upon it to do all the work for you. I'm not quite sure your calculator, well, it might be able to do this. I'm going to pause, you work through it, and I'm going to see if it actually works with the calculator. All righty, let's see how well you did here. And by the way, it does work. I did it there and I got the answer. So I'm not encouraging you to cheat. I'm just encouraging you to use all of your resources, and I'm not testing you on this anyway, so it doesn't matter. When you get into high school, probably science class might be where you see stuff like this. And I guarantee you your science teacher is going to encourage you to use your calculators. All right, so first things first, we cannot add those together until they have the same power of 10. So I would encourage you to borrow a power of 10 from this and move it over to here so that becomes 0.124 times 10 to the 4th. And then we're going to add that to 2.3 times 10 to the 4th. Then when we add everything together, we get 2.424 times 10 to the 4th ends up being our solution, which, by the way, 10 to the 4th is 10,000, so this is 24,240, which, if you look here, if you see how I typed everything in, and then I hit the enter button, 24,240 is the correct answer. Now, this gave it to us in standard form, not in scientific notation, but you could convert that without too much trouble. Here, 4 times 10 to the 5th divided by 8 times 10 to the 7th. I'm going to take 4 divided by 8, which I know is 1/2, and 10 divided by, or 10 to the 5th divided by 10 to the 7th, which is going to result, if we write this as a negative exponent, as 10 to the negative 2nd, or 1 over 100, or 1 over 10 to the 2nd. So if I write this as 0.5 times 10 to the negative 2nd, we have now learned that this is equivalent. Oh, I guess we're keeping it in scientific notation, aren't we? Okay, I see what we're doing. I was thinking we might multiply that and get a decimal number of 0.005, but that's eventually what we would get here. But we have to take, and that's not in scientific notation, so let's put it back into scientific notation by taking a power of 10. Oh, this is confusing. All right, let's do this. Hold on. This is what we would probably need to do here. I'm doing it mentally because I know what's going on, but you probably are confused at this point. This cannot be how we write our answer. So this literally means 0.5 times 0.01, which when we take 5 times 1, you get 5 for an answer, and then 1, 2, 3 decimal places. That is the answer in standard form. And if you wrote that, I guess they didn't technically tell us to write our answer in scientific notation. You probably could get away with answering it like this. But at this point, we want to identify what place is that digit in. It's in the 3rd decimal place, so it's going to be 5 times 10 to the negative 3rd power. That would be the way to write this as in scientific notation. And then the last problem involves multiplication. So we're going to take 8.5 times 7.6. That ends up being 64.6. and then 10 tenths times 10 to the 12th is 10 to the 22nd. This is not in scientific notation, however. So let's take a power of 10 from the 64.6 and turn that into 6.46, and then we'll add the power of 10 to the 10 to the 22nd to make it 10 to the 23rd. And I believe that is where we end today's lesson. Does that seem like a lot? It is a lot, and I apologize for that, but you know, we just need to practice it. It's going to show up in the homework. It'll show up on an assessment tomorrow on Friday, and it's going to show up on the study guides. You're going to have plenty of time to practice it. Good luck. I told you, this can be a little bit complicated. Just do your best, and I don't know, maybe I won't put this on a test, but I feel like I should put at least one of them on the test. We'll see. All right, here, bye.
Hey, feeling good, like I should. When in dark,